In this video, we're going to work on solving some diode circuit problems. So for each of these circuits, calculate the output voltage and the current flowing through the resistors. Now the first thing we need to determine is if the diode is on or in the off state. The silicon diode requires a voltage of about 0.7 volts to activate it. So there's enough energy in these batteries to turn on the silicon diode. Now for the circuit on the left, the current, which flows from the positive terminal to the negative terminal, that is the conventional current. Keep in mind electron flow is in the opposite direction. But in the direction of conventional current, this silicon diode will be on. The other one is in the opposite polarity. It's not connected properly, so this particular diode will be off. So there's nothing we could really do with this circuit. So the output voltage will be 0. And there's going to be no current in this circuit, so the current is 0. But now let's focus on the circuit on the left. We can assign the ground as a potential of 0. The potential at this point will be 12. The silicon diode has a voltage drop of 0.7. 12 minus 0.7 will give us an output voltage of 11.3. So that's the first answer for the first problem. The next thing we need to do is calculate the current in the circuit. The current is going to be the voltage across the resistor divided by the resistance. So there's a voltage drop of 11.3 volts across that resistor. The resistance is 5 kilo ohms. So 11.3 divided by 5 is 2.26. So you should get 2.26 milliamps. Now let's work on another problem. Go ahead and calculate the output voltage and the current flowing through the 4 kilo ohm resistor. So first, let's identify the different points in the circuit. Let's call this point A, point B, point C, and point D. So the ground is at a potential of 0. The potential at point A with respect to the ground is 9 volts. In order to activate the silicon diode, we need a voltage drop of 0.7. And there's enough energy to activate both the silicon and the germanium diode. And the current is flowing in the right direction. So both of these diodes will be in the on state. Now the potential at point B will be 9 volts minus the voltage drop of 0.7. So that's going to be 8.3 volts. The germanium diode has a voltage drop of 0.3. So 8.3 minus 0.3 will give us the potential at point C, which is 8 volts. So that is the output voltage for this particular circuit. So now that we have that, we can calculate the current flowing through the resistor. The current is going to be the voltage across the resistor divided by the resistance. So the voltage across the resistor is the difference between the potentials at point C and D. So we have a potential difference of 8 volts. The resistance is 4 kilo ohms. So 8 divided by 4 is going to be 2. Now keep in mind, you're really doing 8 divided by 4,000, which you should get 0.002 amps, which is equal to 2 milliamps. 1 amp is 1,000 milliamps, and 1 milliamp is 0.001 amps. So this is the current that is flowing in this resistor. Here's another example that we could work on. Feel free to pause the video and go ahead and calculate the output voltage and the current flowing through the 5 kilo ohm resistor. So the first thing we need to determine is if the diodes are on or off. The current is flowing in the right direction, which is good. And the battery has enough power to activate both of those two diodes. Now we have a silicon and a germanium diode, each with a different voltage drop. So one of them is going to be on and the other is going to be off. But let's label our points of interest. So we have point A, point B, and point C. The potential at point C is 0 volts. At A is 6 volts. Now, the germanium diode has a voltage drop of 0.3. So it wants B to be at 5.7. The silicon diode has a voltage drop of 0.7, so it will cause B to have a voltage drop of 5.3. But both of these values can't be correct. One of them is correct. Because the germanium diode requires less energy to be activated, that's the diode that's going to be in the on state. Electricity will always flow in the path of least resistance, and germanium is the diode that offers the path of least resistance. So this diode will be on, while this one will be off. So the potential at point B is 5.7 volts. So that's our first answer. So now we can calculate the current. So it's going to be the voltage divided by the resistance. The voltage across the resistor is 5.7 volts. The resistance is 5 kiloohms. So 5.7 divided by 5, that's going to give us a current of 1.14 milliamps. So that's it for this particular circuit. Go ahead and try this problem. Calculate the output voltage and the current flowing through the 4K resistor. Now we're going to do this two different ways. The quick and simple way, and also the way that you need to do it if you have a test where you have to show your work. So we know that the voltage drop of the silicon diode is 0.7. So 10 minus 0.7 is 9.3. That means that we have a total of 9.3 volts across these two resistors. So we can calculate the current. It's going to be the 9.3 volts across those two resistors divided by the sum of those resistors because they're in series. And that will give us a current, if we round it, to 1.33 milliamps. So now we could find this voltage. So the voltage across the 4K resistor is going to be the current that flows through it times the resistance. So it's 1.33 times 4K, and that will give you an output voltage of 5.32 volts. So that's how we can quickly get the answer if you understand circuits and the way they work. It all comes down to understanding Ohm's law and the voltage drop across diodes. Now let's talk about the other way of getting the answer. So we need to use Kirchoff's voltage law, which states that the sum of the voltages around a closed loop circuit adds up to 0. So let's start from this point. As we travel in this direction, this is a voltage rise. The battery increases the voltage of the circuit by putting energy into it. So that's going to be positive 10. As we travel through this resistor, that's a voltage drop. The resistor consumes energy from the circuit. Now, the voltage drop, keep in mind V equals IR, is going to be the current times the resistance. So the resistance is 3, the current is I. There's only one path for the current to flow, and that's in this direction. So we could just call the current I. As we flow through the diode, or as the current flows through the diode rather, we can see that we have a voltage drop of 0.7. So the circuit loses 0.7 joules per coulomb, or 0.7 volts. Now flowing through this resistor, that's another voltage drop, but it's going to be 4 times I. And so now that we've completed the loop, we're going to set this equal to 0. So we have 10 minus 0.7, which is the 9.3 that we have here. And then if we add like terms, this is going to be negative 7i, and that is equal to 0. Moving this to the other side, we have 9.3 is equal to 7i. Dividing both sides by 7, you can see we're going to get the same answer. (9.3 over 7), that's going to be 1.33 milliamps. Now once you have the current, you could just use this formula to get the voltage of 5.32. So that's how you could show your work in getting the current for this particular circuit. Go ahead and try this problem. Calculate the output voltage and the current flowing through each diode. So the current is flowing in the right direction, and the battery has enough energy to activate these diodes. So both diodes will be in the on state. Now, let's call this point A, point B, which is the same as that point, and point C. So we're going to assign 0 volts to the ground, which means A will be at a potential of 8 volts. Now, the diode will have a voltage drop of 0.7, so B is at 0.7 volts, which means both diodes are on. So we already have our output voltage. It's 0.7. Now we need to calculate the current. So let's focus on the 3K resistor. I'm not sure what just happened there. Sometimes this computer acts up. So notice that the voltage across the 3K resistor is 7.3. So using this formula to calculate the current flowing through it, it's going to be the voltage or the potential difference between points A and B divided by the resistance. So the high potential is at 8 minus the low potential of 0.7 divided by a current of 3. So we have a voltage of 7.3 divided by the 3 kilo ohm resistor. So the current is 2.43 milliamps. So we got 2.43 milliamps flowing through the resistor. Now that current is going to be split into the two diodes. So 2.43 divided by 2, assuming that both diodes are the same. If they're identical, the current will be 1.215 in both diodes. So that's it for this problem. That's how we can calculate the current through each diode as well as the output voltage. Let's work on this example. Go ahead and calculate the output voltage and the current flowing through the 2K and the 5K resistor. So the current is flowing in the right direction in both diodes. So both diodes are on. The germanium diode has a voltage drop of 0.3 and the silicon diode has a voltage drop of 0.7. Now the voltage across these 2 points is 16 minus negative 8. So 16 minus negative 8 is positive 24. So that's really the voltage across this circuit, or at least across points A and point B. So to calculate the current, it's going to be the voltage, the total voltage across these two resistors, divided by the sum of those resistors since they're in series. So the voltage across those two resistors is going to be 24 minus the voltage drop of the two diodes. And then the total resistance is 7K. So keep in mind, the current is voltage over resistance. So 24 minus 0.7 minus 0.3, that's going to be 23. And so we got to divide 23 volts by 7K. And so the current flowing in the circuit is 3.286 milliamps. Now for those of you who want to show your work the proper way, here's what you can do. So we're going to start from the high potential. So we have positive 16, a voltage drop of 0.3. Going through this resistor is going to be minus 2 times the current. Then going through the silicon diode, it's going to be minus 0.7. And then going through the 5 kilo ohm resistor, it's going to be 5 times I. And then minus, we have a negative 8 voltage potential. And then that's going to equal 0. So we have 16 minus 0.3 minus 0.7, that's 15, plus 8, that's 23. And then we have negative 2i minus 5i, which is negative 7i. So 23 is equal to 7i. Dividing both sides by 7, we can see that I is 23 over 7, which gives us the same answer. So now that we have the current, let's calculate the output voltage. But let's calculate the voltage across every element, or the potential at each point. So the potential at A is 16. The potential at B has to be 16 minus 0.3, which is 15.7. Now there's two ways we can calculate the potential at C. We can start with this value. So it's going to be 15.7 minus the voltage drop of that resistor. So the voltage drop is going to be I times R, which we really don't know what, well, we do have the value of I. So it's going to be 3.286 milliamps times the 2 kilo ohm resistor. So at point C, the voltage is 9.128. So that's one way in which you can get the answer. The other way is going up this way. So let's calculate the potential at D starting from B. So B is at negative 8. The potential at D is higher than B because the current is flowing from D to B. Conventional current will always flow in the direction from high potential to low potential. So D is at a higher potential. So to get the potential at D, because we're going up against the current, we need to add as opposed to subtract. So it's going to be the current flowing through the 5 kilo ohm resistor, which is this number again, times 5 kilo ohms. So negative 8 plus 3.286 times 5, that will give us the potential at point D, which is 8.43 volts. So now to get the potential at point C, we need to add these two numbers. So 8.43 plus 0.7 gives us 9.13. So these two answers are approximately the same. The difference is due to the rounding that I've made with this current value. So we could say that the output voltage is approximately 9.13 because both numbers round to that value. So that's it for this particular problem. Here's another one for you. Let's say both of these are silicon diodes. What is the output voltage and the current flowing through the 6 kilo ohm resistor? Go ahead and try it. So both diodes have the potential to be on. The current is flowing in the right direction, and the potential difference between those two values and these two values exceed 0.7. Now let's call this point A, point B. Now at point A, due to this silicon diode, the potential should be 4.3. And at point A, due to this silicon diode and the 12 volt potential, it should be 12 minus 0.3 or 11.3. Now, because of this, we can't have two different values. One of these values will be correct. So the higher potential is going to win out against the lower potential. So therefore, it's going to be 11.3. This diode will be on, and the other one will be off. So now we can calculate the current flowing through the 6 kilo ohm resistor. And we know that the output voltage is 11.3. So the current is going to be the voltage across the resistor divided by the resistance. And the voltage across it will be VA minus VB, since the current is flowing from A to B. So the potential at point A is 11.3 minus the potential at point B, which is negative 3, divided by 6 kilo ohms. So the voltage is going to be 14.3 volts. And if we divide that by 6, that will give us a current of 2.38 milliamps. So that is the current flowing through the resistor. And because this diode is off, the current flowing through this diode, all of it will be 2.38 milliamps. So that's it for this problem. So here we have a challenge problem. Go ahead and calculate the current flowing through each resistor as well as the output voltage. So let's call this point A, and this is going to be point B, point C, point D, and point E. Both silicon diodes will be in the on state, so they will both have a voltage drop of 0.7. 12 minus 0.7 is 11.3. So the potential at point B and C are the same. Because of that, we can treat the 2 kilo ohm resistor and the 4 kilo ohm resistor as if they're parallel to each other, because they have the same voltage across it. To calculate the equivalent resistance of two resistors in parallel, you could use this formula. So it's going to be 1 over 2 plus 1 over 4 raised to the minus 1. And that should give you 4 over 3, or 1.33. So these two resistors in parallel are in series with the 8 kilo ohm resistor. So the total resistance is 8 plus 1.33, which is 9.33 ohms. And we know the potential between these two resistors in parallel and that resistor in series. It's going to be the difference between point B and point E. So the current, the total current flowing in this resistor, which is the two currents, the sum of the two currents flowing in those resistors, it's going to be the voltage between points B and E divided by the total resistance. So that is 11.3 minus negative 9, and the total resistance is 9.33. So that's 11.3 plus 9, which is 20.3, divided by 9.33. This gives us a current of 2.18 milliamps, and that is a rounded value. So that is the current that is flowing through the 8 kilo ohm resistor. Now, how much current is flowing through the 2 kilo ohm resistor and the 4 kilo ohm resistor? We can't just divide them by 2 because the resistor values are different. So what should we do in this case? When you have two resistors in parallel to each other, that is that they have the same voltage across each other, let's call this R1 and R2. If you know the total current that is either entering that branch or that is leaving that branch, you can calculate the currents flowing through each resistor. To calculate I1, it's going to be the total current times the other resistor, which is R2, divided by the sum of those two resistors. So in this case, to calculate the current flowing in that resistor, it's going to be the other resistor, 4 kilo ohms, divided by the sum of the two resistors, 4 plus 2, times the total current that is either entering or leaving that branch, which we could see it's 2.18. So it's going to be 4 over 6 times 2.18. So the current that is flowing through the 2 kilo ohm resistor is approximately 1.45 milliamps. Now the current that's flowing through the 4 kilo ohm resistor, we can do 2.18 minus 1.45, and that's going to give us 0.73 milliamps. Or we could use the formula. It's going to be the other resistor, which is 2, divided by the sum of the two resistors, times 2.18. So that's 2 over 6 times 2.18, and that'll give you the same answer, 0.7267, which rounds to 0.73. So that's how you can calculate the currents flowing through those two resistors. Now, if you want to check your work, here's what you can do. Let's calculate the potential at point D two ways to make sure our work is correct. So let's start with the potential at point B, which is 11.3, and let's subtract it by the voltage drop of that resistor, which is the resistance of 2 kilo ohms times the current of 1.45 milliamps. So 11.3 minus 2 times 1.45, that gives us a potential of 8.4 volts. So we can also get that answer going through this branch from point C to point D. So the potential at point C is 11.3. We have a 4 kilo ohm resistor and a current of 0.73 milliamps. And that gives us 8.38, which rounds to 8.4. Now let's go this way to calculate the potential at point D. So we're going to start with the negative 9 volts. Now we're going against the current through the resistor, so we got to add the voltage drop. So the current flowing through that resistor is 2.18, as we could see here, times the 8 kilo ohm resistor. So it's negative 9 plus 2.18 times 8, and that gives us 8.44. In all cases, we could say that the output voltage is approximately 8.4 volts. So as we can see, the math makes sense. So that's it for this video. Now you know how to solve diode circuit problems.